Well, my dear participants, today I am going to talk about uh, how we can make simulation from chi-square with 30 degrees of freedom. So, first we are taking why 30 degrees of freedom, because we expect that it is to be more close towards normal, more close towards normal. So here, mm, chi-square with 30 degrees of freedom, we expect it to be approximately normal. So chi sq 30 replicate expression here 30 and see d chi sq df is equal to. So here we have added mm, the exact normal curve on the simulated data. So certainly this will match the distribution. But if we can talk in terms of mm, central limit theorem, we have to go in terms of the here these things will be same, but we have to approximate. It is not about central limit theorem, it is about the simulation from simulation from to look into the central limit effect. Central limit effect when df is equal to 30. So here we can paste these commands. But see what happens. We are making histogram, but here curve should be d norm. To look into the central limit theorem, curve should be d norm x, and here not degree of freedom, it is mean. So for a chi-square distribution with 30 degrees of freedom, the mean is equal to 30, the degree of freedom, and SD is equal to SQRT twice into 30. So it should match with the distribution. When we run this, see here, this is the chi-square distribution which we are simulating, and we are adding this normal curve on it. We are not adding here, we have added chi-square, we have simulated observations, and then we have added the exact chi-square distribution. But here we are adding on the histogram which is based on the simulated data from chi-square with 30 degrees of freedom, a normal curve, because we want to see the central limit effect. But here again we find that central limit effect is not very good, because distribution is right skewed and here the function is symmetric. So normal approximation does not work well, even despite the fact that the degree of freedom is 30. When we make a smaller degree of freedom, say for example 3, so see what happens about. So here we are just making 3, and here it should be 3, mean should be 3, and SD should be 2 into 3. Now see what happens. See, here situation is more bad, because here our central limit theorem says that if degree of freedom approaches to infinity, then only this chi-square distribution can be approximated by a normal distribution. But here degree of freedom is very small, and that's why we are getting here this is the normal distribution and this is the chi-square distribution with 3 degrees of freedom. So there is no match. It is very bad approximation. Whereas in case of 30, see what happens. 30 here, and we are making 30 here, and then 30 here, and then 2 into 30 here. So in this situation, central limit effect is better. So here it approximates better, in a better manner. So this was all about central limit effect when parent population is chi-square distribution. Some problems I am going to discuss. See, some problems with chi-square distribution. Question number 1. See, I would like to read in the PDF. Some problems with chi-square distribution. Let x1, x2 be independent chi-square random variables with R1 and R2 degrees of freedom respectively. Show that U is equal to x1 by x1 plus x2 has a beta distribution with shape 1 is equal to R1 by 2 and shape 2 is equal to R2 by 2. And V is equal to x2 by x1 plus x2. Here x1 is in the numerator, but here x2 is in the numerator. So here what it affects, shape 1 is equal to R2 by 2 and shape 2 is equal to R1 by 2. So here this has the effect on these things. So if we run, we are trying to solve this equation. See, x1 R chi SQ 1000 df is equal to 10, x2 is equal to R chi SQ df is equal to 12. So here we are simulating 1000 observations from the chi-square distribution with 10 degrees of freedom. In x2 we are simulating 1000 observations with the degree of freedom 12, and then we are going to define a new variable u is equal to x1 upon x1 plus x2, another variable v is equal to x2 divided by x1 plus x2, and then we are making the histogram of u. So it should be curve d beta, because it is beta distribution, d beta x 10 by 2, R1 by 2 and R2 by 2, add is equal to true. So this generates this graph. See, they are very close, so that means it verifies the result of sampling distribution, and that distribution, that result is this one, and that is if x1 and x2 are chi-square distributions with R1 and R2 degrees of freedom, u is equal to x1 by x1 plus x2 follows beta distribution with shape is equal to R1 by 2 and R2 by 2. Whereas V is equal to X2 divided by X1 plus X2 has a beta distribution with shape 1 is equal to R2 by 2 and shape 2 is equal to R1 by 2. So this result has been verified here because it matches well. So that means the histogram and the exact probability curve, they are matching. That means our result, which we normally derive through analytic derivations, and that has been proved by the simulation using R. So that is an excellent part of R, that we are talking of sampling distribution throughout, but we are not making any analytical result. We are not using calculus or we are not using mathematical derivation. Rather, we are trying to prove these results through simulation using R. So this is the another advantage. Now what happens about V? V is nothing but when V is equal to X2. X2 in the numerator. Here X1 was in the numerator. So when X2 goes in the numerator, the first shape 1 is equal to R2 by 2 and R1 by 2 is the second shape. So this is the shape parameter change. So this is another, see, it is 12 by 2, 10 by 2. So here again we have an excellent match between the simulated data and exact result, exact curve, which is being plotted on the basis of exact beta distribution with these parameters. So this verifies the facts. See, question number 2. See, another result we have verified, which is very famous in statistical inference in sampling distribution, that before coming on this result, I would like to run these commands here. See, these are the commands and we run these and we are getting the results. Similarly, see, this is the distribution of V, and where is the distribution of U? Distribution of U is this one. So this is the distribution of U and this is the distribution of V. Both the graphs we have kept in the same. In U, the curve d beta is x 10 by 2, 12 by 2. Whereas in case of V, here shape 1 is equal to 12 by 2 and shape 2 is equal to 10 by 2. So this is the interchange of the shapes degree of freedom. Now I would like to discuss another result, and that is, I have taken this exercise from George Casella and Berger's, a very famous book on statistical inference. Its title is Statistical Inference by George Casella and R.L. Berger. George Casella and R.L. Berger. So that is an excellent book to read, to understand sampling distribution, to understand inference. So I have taken this is a result which is given in George Casella and Berger. Here, if W follows F distribution with degree of freedom df1 R1, df2 R2, show that Z is equal to R1 by R2 into W divided by 1 plus R1 by R2 into W has a beta distribution with when shape is equal to R1 by 2 and shape 2 is equal to R2 by 2. So we have proved this result. W is equal to RF. RF stands for random simulation from F distribution, RF. R norm, random simulation from normal distribution. R poise, random simulation from Poisson distribution. R chi-sq, random simulation from chi-square distribution. Similarly, RT, random simulation from the T distribution. So here RF means random simulation from F distribution. So 1000 observations are being simulated, and degree of freedom is 10, and degree of freedom 1 in numerator, degree of freedom is 10, and denominator degree of freedom is 12. Now we are defining the expression Z is equal to 10 by 12 into W divided by 1 plus 10 by 12 into W. And then we are making a histogram of Z prob is equal to true, and we are adding a beta curve with shape 1 is equal to 10 by 2, shape 2 is equal to 12 by 2 on the same. So here it is cutting this part. We can improve this. Just we can improve this. We can remove this. Go into the command. So here if we run this, here it is good. Otherwise, if we want to improve the Y limb, we can have here Y limb is equal to C 0, minimum limit 0, and say 2.5. The upper limit is 2.5. So Y limb it will increase from 0 to 2.5. So if we make this change, see what happens. See, here it improves to some extent. So a better picture comes. And so this way we are verifying this result, and the result is what? Result is this. Result is that if W follows F distribution with R1 and R2 degree of freedom, then the distribution of Z is equal to R1 by R2 into W divided by 1 plus R1 by R2 into W has a beta distribution. So this result get verified without making analytical derivation. We are proving this result through simulation. So this way we can prove these results. Now I shall talk about students' T distribution with 5 degrees of freedom. See, student's contribution is very good. His original name was William Seeley Gossett, and he published his papers on student T distribution in 1907 and 8. And you know what is the story behind student? He was working as a quality control analyst in a brewery company in Dublin, and company does not allow him to publish any paper. So he preferred his pen name student. Otherwise his name was William Seeley Gossett. So, and that's why it's student T. So if T is equal to Z by square root of X by K follows T distribution, then it is termed as student's T distribution with K degrees of freedom. It may be noted that this Z follows normal 0, 1, whereas this X follows chi-square with K degrees of freedom, that is chi-square with K degrees of freedom. It must be noted that both Z and X are independent random variables. We implement this sampling distribution with K is equal to 5 degrees of freedom as C. What we are doing? T5, T with 5 degrees of freedom. Replicate, N is equal to 1000, expression, R norm. R norm 1 means we are simulating a standard normal variate single sample from Z and divided by square T R chi SQ with 5 degrees of freedom, and we are dividing it by the degree of freedom. So this way we are simulating each time a random sample from T distribution with 5 degrees of freedom. And how many times we are repeating this process? 1000 times. So we have 1000 T5 random variates. And then we are making a histogram of T5 with prob is equal to true, y lim is equal to C 0.5 and x lim. Here we are putting a limit on x-axis -5 to +5. And curve dt, here this is the exact curve, dt x df is equal to 5, add is equal to true. So see, this histogram is made on the simulated data, whereas this curve is exact curve of T distribution. So both are matching together. So that means our simulation is very much correct. And see, note that histogram is constructed on simulated values using replicate, whereas density curve is exact T with 5 degrees of freedom. However, both are matching with, which is an indication of the fact that both follows T distribution with 5 degrees of freedom. Suppose instead of 5 degrees of freedom, suppose we simulate observations from 100 degrees of freedom. So see what will happen and what will be the effect on the result. So I will go on here. See, this is T5 with 5 degrees of freedom. So what we can do? We can have T100 R norm. So here it will be df is equal to 100 divided by 5. So here we can make changes. Just I am going to write an expression here. Or even we can make changes here like T100 replicate R norm R chi SQ df is equal to 100, and we have to divide it by 100. Now prob T100 ठीक है. Now we will add degree of freedom instead of 500 here, and we can see what happens. We can make these modifications and see. Here it is very close to normal distribution. It is very close to normal distribution. Say if we add a normal curve on it, we can have curve d norm x, ठीक है, d norm x and add is equal to true and cull is equal to red. Cull is equal to red. So we can add a normal curve on this. See, if we run these commands, see, it is very difficult to distinguish a normal distribution and a T distribution with 100 degrees of freedom. They are very so close. They are so close that we cannot distinguish them. See, if we change the color of this one of the T distribution, col is equal to blue. See what happens. See, both are matching. Both are matching. It is very difficult to identify them, to distinguish the. And this is an excellent result of the theory, and that theory says that if n tends to infinity, T distribution can be approximated well by a normal distribution. So here this theorem, this result we are proving through simulation. Now, in my tomorrow's talk, I shall talk about F distribution and its relation with some other distributions, the relation between T and F, and a relation between gamma and beta, and sampling distribution of S square, etc. So these things I shall talk in my tomorrow's lecture. So that's all for today.